CDMA or Code Division Multiple Access. We want to use the same channel to send multiple signals at a time. So this is a multiplexing scheme, but it is quite different from other the schemes which we have seen. Here we have a code, very important aspect in this code division multiplexing. The first word is a code. So code division multiplexing is a form of spread spectrum communication. Spread spectrum means all the spectrum will be used by all the signals all the time. So this is a form of spread spectrum communication in which a narrow band signal is spread out over a wider frequency band. This CDMA is more tolerant to interference as compared to other schemes, and multiple signals, they share the same frequency band. So each station, each signal will transmit over entire frequency, and all the time. That is, this signal will use whole frequency band or the spectrum allocated and all the time. The only difference is the coding theory. So time it will get, frequency it will get, every signal every time. The key difference is the code. How does it work? Let me give you a real life example. Just imagine an airport lounge with different people conversing. Let us say two people are conversing. Many pairs are conversing. They have different ethnicity, they have different languages. When we talk about the time division multiplexing, you can assume that the pairs of people, that is two people at a time, they are talking in turns. That is, when two people are talking, others are not talking. Then the other will get the time. Likewise, then we have FDM, frequency division multiplexing. You can imagine now the people or now the pairs are talking in different tone, different pitches. Some are talking in high pitched, say some are low pitched talking. When we are discussing the CDMA, every pair is talking at once. Everyone is talking, but in a different language. One is talking in Chinese, then French, then Hindi or Urdu. So the key to CDMA is to be able to extract the desired signal, because multiple signals are being sent on the channel. So the receiver must extract the required signal, desired signal, and reject every other signal as a random noise. This is CDMA. So we will use the special code. Every station will get a special code, and this code will be generated by, or they are called as Walsh codes, which are orthogonal combination of ones and zeros. We'll call them as chip sequence, chip pattern. And chip duration is much shorter than the symbol period. Let me tell you again, all users send and receive data at the same time, at the same frequency, but in codes. In CDMA, each bit time is divided into M short interval called chips. Each bit time into M short interval, which are multiplied against the original data sequence. Let us say we have a station. We give it a proper unique code sequence, chip sequence. Let us say a 4-bit chip sequence is like this. I'm taking any arbitrary value. I'll tell you why this 1 minus 1 has come. This 1 minus 1 has come from the Walsh coding. The data may be, say, -1, +1. Okay, -1 or 0, sorry. The data can be 1, -1, 0. What do you want to say? What bit you have said? Okay. So the inversion will send 0. The actual bit sequence will send 1. Typically, there are 64 to 128 chips per bit. But for simplicity, we will stick to 8-bit. We'll take one more example that will have these 4 bits, and we'll take the whole sequence of step. But in order to understand, we are taking right now 8 chips per bit. So each station, as I said, will be assigned a very unique M-bit code, which you see here also, is called a chip sequence. And the codes, if you see, they're only represented by a -1 or a +1. Every code will be either -1 or +1. So in order to send a 1 bit, the station will do what? It will send the chip sequence being assigned to that code, because if -1, 1, 1, 1 is there, it will send the same sequence if a station wants to transmit a 1. Okay. Now what about 0? If a 0 bit has to be transferred, the same chip sequence will be complemented, or the negation of this chip sequence will be done. Just multiply everything with a -1. That is, take the complement. So in order to send a 1 bit, the original chip sequence, 0, the negation. As I'm saying, we are just taking the 8 chips per bit. So let us take a station A sending some chip sequence. Now here I'm showing you the 4, not 4, but the 8-bit chip sequence. As I said, it can go up to 64, 128. So if the station want to send a 1, it will send the same chip bit sequence. But if a station want to send a 0, it will just negate it, that is complemented. You see, both these chip sequence are nothing but the complement of each other. But I am trying to suggest you that these are not the bit sequence, they are voltage levels. That is the +1 volt and -1 volt, for example. So actually in your mind you have to keep that you are sending the voltages. Here we have 4 stations and 8-bit per chip sequence has been given. And you know this chip sequence has come from Walsh code. Now increasing the amount to be sent from say B bits per second to M times, that is the MB chips per second, for each station, that A, B, C, D we are signifying for each station, means that the bandwidth needed for CDMA is a factor or is greater by a factor of M than the bandwidth which are not those stations not using CDMA. For example, if we have a 1 megahertz band available for 100 stations, 1 megahertz for 100 stations. If you are using the FDM or frequency division multiplexing, each one would have 10 kilohertz. That is, you are going to divide the frequency, and then this could be every station will be able to send at 10 kbps, assuming the 1 bit per hertz is there. When you're using the CDMA, code division multiplex access, each station is going to use whole of 1 megahertz. Full 1 megahertz, so the chip rate is 100 chips per bit to spread the station bit rate of 10 kbps across the channel. Across the channel, every station will use all 1 megahertz. So in the chip sequence ABCD, we have assigned to 4 example stations and the signals that they represent. These are 8-bit per chip sequence. Arbitrary chip sequence we have given, but these will have a special property. 2 stations will not have the same chip sequence. Each station has its own unique chip sequence. Okay, S1, S2, S3, S4. These are 4 stations. A, B, C, D are the chip sequence. Let us say S is the M chip vector for station S. S dash is negation. So when it will send +1, it will send the, say A is sending. When it is sending 0, it will send the negation. As I said, all chip sequences are pairwise orthogonal. That is, the inner product of any 2 chip sequence S and T will be S dot T equals 0. What does it mean? Let us take A and B. -1 into -1, 1. -1 into -1, 1. -1 into 1, -1. And 1 into 1, 1. -1 into 1, -1. 1 into 1, 1. 1 into -1, 1. So what I am trying to suggest here is first element of the code sequence multiplied by the second element of the different code sequence. Likewise, and then you add them. That is -1 into -1 plus -1 into -1 like this. So when you add this, it has to go to a 0. It will give you a 0. It has to give you a 0. That is, even if you take B dot C, the inner product, it will give you 0. So all the chip sequence are pairwise orthogonal. And these codes are coming from Walsh code. These are the Walsh code to generate such orthogonal chip sequence. As I said, 64, 124 bit will be there. How do you represent the orthogonality? If you take these two, B and C, -1 into -1, plus -1 into 1, like this, last -1 into -1. So you add them. That will give you 0. So this here is the expression. Then the normalized inner product of any chip sequence with itself will be 1. But what about the station? Okay. If you take A dot A, inner dot product, as I said, because each of the M terms in the inner product is 1, so the sum will be M. That is what the station means. S dot S dash, that is, you take one and the negation of the other, it will give you this scenario. Now, during each bit, a station can transmit a 1. It can transmit a 0. 1 means it is sending its chip sequence. Or 0, that means it is sending the negative of its chip sequence. Or even it can be silent. Any station can be idle. So when two or more stations, they are transmitting simultaneously, their bipolar sequence add linearly. That is, you will take the pairwise 1 by 1 dot product and just add them. For example, if one chip period, 3 station output 1. For example, A, B, C are sending 1. The D station is sending a -1. Just add them. What do you get? You will get a +2. This will be received. This will be sent to the channel. Just assume them as a signal that they are just adding the voltages superimposed on the channel. So in terms of voltage, if 3 stations are sending +1 volt, 1 station is sending -1 volt, so it will be 3 minus 1, which is 2. So 2 volt will be received. Okay. It's all voltage. Nothing is there. All voltage. Now you see from S1 to S6, 6 examples of one or more station, they are transmitting 1 bit at the same time. So first example is S1 equal to 6. That is, only C transmit a 1 bit. So we will just get the chip sequence of C. What is the chip sequence of C? -1, 1, -1, 1, 1, 1, -1, -1. In the second example, S2, both B and C are transmitting 1. So what do? We will take the pairwise combination and addition of these 1 bit. How do you do? -1, -1 is -2. -1, 1 is 0. So whole like this. Last one is -1, -1. That will be -2. You got the idea? How do we get? -1, -1. You multiply and then write. Then add and then write. This is how. And finally, you have to write the sequence. In order to recover the bit stream, receiver must know the station chip sequence in advance. If A is sending something, the receiver of A need to know what is the actual sequence. So recovery is done by computing again the normalized inner product of the received chip sequence and the chip sequence of the station. That is the content in the channel multiplied by the chip sequence of that particular station, and you have to divide by the number of stations. Okay, I'll give you an example. For example, 2 stations A and C. Now they are transmitting 1 bit at the same time. A is sending 1, C is sending 1, and B is transmitting a 0. So what do? First you have to take the sum of A, C, and since B is sending 0, you have to take the B complement. Okay, pairwise. So A and C chip sequence, B will be all the negation complement. So what do you get? Then this, whatever you get, you have to multiply it with the C. If C receiver wants to know, then you have to multiply whole with the C, okay, dot C. Suppose that the receiver, as I said, wants to know what C has sent. So what we will do? We will use this addition and then just multiply it with the code sequence of C. For 2 to the power n station, Walsh code can provide 2 to the power n orthogonal chip sequence of length 2 to the power n. Now let me show you the exact example. We are taking an example of Cdma or code division multiple access. C is for chip pattern. Chip pattern means the unique code assigned to an individual station. Every station is assigned a unique chip sequence called as chip pattern. Two machines will not have same chip sequence. Wherever you see D, that will be data bits. So there are properties related with this chip pattern. Before that, when you are going to send 0, we will use -1. When we will send 1, we will use +1. For example, there is a code. This code we have used 4 only for simplicity. It can be 4, 16, 64. It can go above. So -1, 1, 1, -1 we have taken. So this is a chip pattern or chip sequence. When we are sending 1, we will send this. If you are sending 0, then the same machine will complement it. That is, it will make it as +1, -1, -1 and +1. So complement will be sent. Okay. Now we are ready for the actual example. Let us assume we have 4 stations. Station 1, station 2, station number 3 and station number 4. As I said, every station will be assigned a code, and depending upon the code, they will send the data. They send the data on a single channel. That is why we are calling it as code division multiple access. So let us take the example. We are again taking only 4 of these. It can go beyond 64, 20, 128. So say C1 is 1, 1, 1, 1. C2 is 1, -1, 1, -1. C3 is 1, 1, -1, -1. And C4, 1, -1, -1, 1. These are the chip pattern or the unique chip sequence of 4 machines or 4 stations. So what are the properties? The first property is that if any pair you take and you take the inner dot product, then you need to get a 0. That is, you just have to take the dot product of the pair. Okay, I'll give you an example. Let us take C1 and C4. Now C1 is 1, 1, 1, 1 and C4 is 1, -1, -1, 1. We are taking the code assigned to C1, C4, that is station 1 and station 4. Now what do you multiply this 1 with 1? What do you get? 1. Now multiply the second one. That is 1 into -1 is -1. Third one, 1 with -1 is -1. Fourth one, 1 with 1 is 1. Now you add them. When you add, you will get a 0. You take any pair of these code sequence and you take an inner dot product. It should show the orthogonality pairwise. The second important thing is if you multiply the code of a station with itself, it should get, or you should get, the number of stations. What does it mean? Let us take now C3. Now let us take the dot product of C3 and C3, inner dot product. So we have C3, the code is 1, 1, -1, -1. Then we have again same thing, 1, 1, -1, -1. Now take 1 into 1 is 1. 1 into 1 is again 1. -1 into -1 is 1. -1 into -1 is -1. Just add them. What do you get? 4. How many stations are there? 4. So now both the conditions are fulfilled. You can only give code when they fulfill this condition. Right? The necessary and sufficient condition is done. Now we have to send the data. Let us say station 1 is sending data as -1. As I said, D will represent data with bits. D2 is sending +1. D3 is sending -1 and D4 is sending 1. Now how do we send it? So when the state, because all of them are going to send together. So we have to multiply C1 with D1. So C1, the data has to multiply with the code, then only it will come to the channel. That is, we will multiply -1 with C1. So multiply -1 with every element, 4 element we have. Then we will multiply C2, D2, same thing, C3, D3 and C4, D4. And then we are going to add it. And the resultant will go to the channel, to the transmission medium. So let me just do it. C1, D1. What is C1? 1, 1, 1, 1. What is D1? -1. So all will be negative. So it will be -1. I'm multiplying each code with -1. So -1. Now C2, D2. Now 1 into 1 is 1. -1 into 1 is, so same thing will come because multiplying with 1. Same thing will come. Now C3, D3. Now we are multiplying the C3 with -1. So all will be inverted. You will get -1, -1, 1 and 1. Now same thing with C4, D4. Now we're multiplying 1 with the code. So same thing will come. 1, -1, -1 and 1. Okay. Now we're done with this. Now you have to add it. So now add pairwise or 4 quad wise. You add this -1, 1, -1, 1, 0. Now -1 4 times, you get -4. Again, -1, 1, 1 and -1, it will be 0. Then fourth one, -1, -1, 1 and 1. Again, you will get a 0. So this is the final content that is going to go in the channel. 0, -4, 0 and 0. Okay. So this is going to go. Okay. Now the sending is done. What about retrieval? The retrieval, the receiver has to have the code already known to itself in advance. Okay, we will multiply the code with the channel data and will divide it with the number of station. You will get the bit what is being sent. Let us start. 0, -4, 0, 0 was there. Now let us say the receiver 1 wants what the station 1 has sent. So this receiver wants to know what the station 1 has sent. What is in this code? So what we'll do? We will take the channel data 0, -4, 0, 0. And since the receiver already know the code of station 1, which is 1, 1, 1, 1, we have to take the inner product, dot product. What it will be? See, 1 by 1. 0 into 1, 0. -4 into 1, -4. 0 into 1, again 0. 0 into 1, 0. Now you have to add them. Just add them. What do you get? -4. Now what you have to do? You have to divide it by the number of stations. There are 4. So divide by 4. What do you get? You get a -1. And this -1 was sent by the station 1. Okay. This you have to do for every station. This is how the code division multiple access work. This is an easy scenario, but in practice, it goes for a long code. Thank you so much.